a standard cell. A standard cell is one in which each half cell is made with its electrodes immersed into an aqueous solution with salt having 1.0 mole per liter at STP conditions. For the cell that we have just discussed, it will be a zinc rod immersed into a 1.0 mole per liter zinc nitrate solution in one half cell, and a silver rod immersed in a 1.0 mole per liter silver nitrate solution in the other half cell. And that is what is called a standard cell. Standard cell potential, delta E prime 0. If a galvanic cell is created using the two half cells mentioned above, the maximum potential difference voltage obtained between its two half cells is called its standard cell potential. Since each electrode creates its own potential, the only way of knowing the standard cell potential is to know the potential of each half cell and then calculate the difference in their potentials when they are connected by a wire and a salt bridge. How can the electrode potential for any half cell be determined? This is achieved by making use of what is called a standard hydrogen half cell. The standard hydrogen half cell is composed of a platinum electrode immersed into a solution that has 1.00 mole per liter hydrogen ions with hydrogen gas at SATP being bubbled over it. So this is a solution that has 1.00 mole per liter hydrogen ion, and here is a tube that is open at the bottom and sealed at the top, but it allows a platinum wire connected to a platinum electrode to pass through it. Into this tube, hydrogen at SATP is bubbled over this platinum electrode here, and this constitutes what is called the standard hydrogen half cell. Scientists have assigned a voltage of 0 to the standard hydrogen half cell, and the electrode potentials of other half cells are measured with reference to it, measuring standard electrode potential. So if you wanted to measure the electrode potential for this zinc half cell, this is what is done. A wire is connected from the zinc electrode to the platinum electrode, but a voltmeter is placed in series with that, and of course a salt bridge is used to connect these two half cells. When these are done, it is noticed that electrons flow in that direction there. And for electron to flow in that direction, it means that this electrode here must have become negatively charged. And for that to become negatively charged, zinc atoms must have ionized to produce zinc ions there, and in the process, leaving electrons behind. Oxidation happens here, and because of that, the zinc electrode is called the anode, and the platinum electrode is called the cathode, because, of course, if oxidation takes place here, reduction happens here. The voltage that is measured by the voltmeter is registered. And this is how the electrode potentials for other half cells can be measured. So that is what explains it there. Same thing. When connected to a zinc half cell, the standard hydrogen half cell is acting as the oxidizer. Since electron flows into it, it does become the cathode, and the zinc electrode becomes the anode. The voltmeter placed in series measured a voltage of 0.67. Since the voltage assigned to the hydrogen half cell is 0, the standard electrode potential of the zinc half cell is 0.6 volt. And that, of course, is a notation given to that cell when a zinc half cell is connected to the hydrogen half cell. When this was done for a silver half cell, the current flows in the opposite direction, and a voltage of 0.80 was measured. The silver electrode became the cathode, and the standard hydrogen half cell became the anode. And this is how the cell notation for that new cell is represented. Next, we do what is called standard reduction potential. Performing similar types of experiments Using different half cells, scientists were able to determine their electrode potentials. However, chemists have decided to label all half reactions as reductions. But not all species undergo reduction. Zinc, for example, undergoes oxidation. Species that undergo oxidation are assigned negative electrode potentials, while those that really undergo reduction are assigned positive electrode potentials. The following table provides a list of a few of these when compared with a standard hydrogen half cell. We can see that from the list given here, for the metals, you can see that their reducing strength increases downwards. And for the ions, you can see that their oxidizing strength increases upwards. Notice how the hydrogen half cell is given a voltage of 0. And anything that undergoes oxidation, as is shown here with these, anything that undergoes oxidation, whatever voltage is measured is given a negative value. And those that undergo reduction will retain their positive values. Calculating standard cell potential. A general equation that is used to calculate standard potential is, that is the standard cell potential symbol is equal to the electrode potential that is produced at the cathode minus that of what is produced at the anode. Or we take the voltage here and subtract that from it. Recall that this was what is produced for silver undergoing reduction, and this was what is produced for zinc undergoing oxidation. This negative here will negate that negative, so the total voltage produced will be equal to 1.56 volts. Since the standard cell potential is positive, the reaction between zinc and silver will be spontaneous. All positive values indicate spontaneity. Negative values indicate non-spontaneity. Supposing that one half cell uses aluminum instead of zinc with a silver half cell, what will be the standard cell potential of the cell produced? Now, instead of zinc, we're using aluminum. And if we go back to the table and see what's the reduction potential for aluminum, we can see that it is negative 1.6. So the new standard cell potential will be equal to 2.4 volts. What would it be for iron and copper? Iron and copper, look. Iron is here, negative, and that is it for copper. And this is what it turns out to be, 0.79 volt. Now listen to this piece here. Notice how the voltage produced depends on the position of the species on the list provided. The farther the oxidizing agent and the reducing agents are apart, the greater is the voltage of the cell produced. The closer they are apart, the smaller is the voltage produced. See? Look. Let's see how far these are apart. These are apart. That's where they are here. Look what happens. When you have aluminum and silver, it was able to produce the highest voltage. So that's the galvanic cell and all of these other features that we've spoken about. Basically, it is made up of two electrodes immersed into an electrolyte that is having cations from which the electrode is made. Silver will have silver ions. The stronger reducing agent gets oxidized, leaving electrodes behind. The stronger oxidizing agent gets reduced by accepting electrons and making this electrode become positively charged when the wire is connected between the two, because this electrode is negatively charged and this one is positively charged. Potential differences created that allows electrons to go in that direction. However, because of a buildup of positive charges here, this solution becomes positively charged that impedes the flow of electron in that direction by holding on to electrons on the rod. The opposite is happening over here. The negative charges are increasing in concentration due to the depletion of positive charges. Because of the negative nature of these charges, they will tend to repel electron that is wanting to come in that direction. And we said to rectify that, a salt bridge is used. Negative ions inform nitrate ions seep through in that direction to neutralize any excess of positive charges that are created by zinc ions. Over this side, positively charged potassium ions are going inside there to replenish positive charges that are depleted. Thank you for listening.